All right, let's dive in. Today, we are pulling back the curtain on the invisible architecture that makes our digital world tick, the OSI model. You might not have heard of it, but it is the secret grammar behind every single email, every website, every cat video you've ever watched. Let's get into it.
I mean, have you ever really stopped to think about that? How does your iPhone send a photo to your friend's Samsung, which they then pull up on their Windows laptop? It honestly feels like it should be impossible, right? But it's not magic. It's all thanks to a shared set of rules. This is the exact problem that networking models were invented to solve.
And the secret ingredient that makes this all work is a little something called a protocol. The best way to think about it is like this. Pilots have a very strict set of rules for talking to air traffic control, right? They use specific words in a specific order to make sure nothing goes wrong. Without those rules, you'd have total chaos in the sky. Well, in the digital world, protocols are what prevent that chaos online.
So, here's our game plan. We're going to start with why we even need these rules in the first place. Then we'll get right into the 7-layer blueprint itself. We're going to travel all the way down the stack, from the apps you use every day, right down to the wires and waves, before we finally look at what the OSI model's real legacy is today.
You know, back in the early days of networking, it was pretty much the Wild West. You had companies like IBM and DEC and a bunch of others all building their own computer systems. And that was cool. But there was one massive problem. They couldn't talk to each other. At all. It was like having a party where every single person spoke a different language. You needed a universal translator. You needed a standard.
So how in the world do you solve a problem that big?
Well, you do what any good engineer does. You break it down into smaller, manageable pieces. Instead of trying to create one giant, complicated set of rules for everything, the solution was to create a stack of layers. Each layer has one very specific job to do, and it just passes its work on to the layer below it. Simple, but brilliant.
And that brings us to the star of today's show. In the late 1970s, a group called the International Organization for Standardization, you probably know them as ISO, developed the Open Systems Interconnection Model. This wasn't a product, it was a blueprint, a universal framework to standardize this whole layered approach to making computers talk to each other.
Now, the real genius of this is its modular design. First off, it makes the whole gigantic process of network communication way easier to understand and troubleshoot. It also created standards, which meant a company like Cisco could build a router, and it would work perfectly with a network card from a completely different company. And maybe most importantly, you could totally revolutionize the technology in one layer, say invent faster Wi-Fi, without having to change a single thing on any of the other layers.
And here they are, all 7 layers in their full glory. We start at the top with application and go all the way down to the physical layer at the bottom. Our journey today is going to be a trip right down this stack, following a piece of data from the moment you create it, all the way down until it becomes ones and zeros flying across a wire. Okay, let's start at the very top with layers 7, 6, and 5. People often call these the upper layers, or the software layers, because they deal with stuff that your software, and you as a user, directly interact with. This is all about getting your data ready for its big trip across the network.
So, layer 7, the application layer. This is the one that's closest to us. Now, it's not the web browser or email client itself, but it's the protocols that those apps use to talk to the network. So when you load a website, your browser is using HTTP. When you send an email, it's using SMTP. This layer is basically the bridge between your applications and the network itself.
Okay, one step down is the presentation layer. I like to think of this as the network's universal translator. See, different computer systems might represent data in slightly different ways. This layer's job is to make sure that when one computer sends an A, the other computer receives an A. It translates everything into a standard common format. It also handles stuff like encryption and data compression.
Next up is the session layer. This is the network's conversation manager. Think about it. When you're logged into your bank's website, you have an open session. This layer is what establishes that connection, keeps it alive while you're doing your thing, and then closes it when you're done. It's like a diligent moderator for the conversation between two computers, making sure everything stays organized.
All right, so our data has been formatted correctly and our conversation is being managed. Now we hit the middle layers. This is where we start packaging up our data and sticking an address on it so it knows where to go. This is also where a really important process called encapsulation begins, which is basically just wrapping our data in a few layers of instructions. Layer 4, the transport layer, is kind of like the network's postal service. It takes that big chunk of data from the upper layers and chops it into smaller pieces called segments. It's all about reliable end-to-end delivery. It can be super reliable, using a protocol called TCP to make sure every single piece arrives perfectly, great for a file download. Or it can be fast, using UDP, which is better for video streaming, where speed is more important than catching every single drop of data.
Now we're at layer 3, the network layer. And if layer 4 was the postal service, this is the GPS. It takes a segment, slaps on a header with the source and destination IP addresses, the unique addresses of the computers on the internet, and turns it into what we call a packet. This is the layer where routers do all their hard work, looking at that destination IP address and figuring out the absolute best path for that packet to take across the maze of the internet.
We are so close. We've reached the last 2 layers. This is where our neatly addressed digital packet gets ready to become an actual physical signal. These layers handle the really nitty-gritty details of getting data across the local network, like from your laptop to your Wi-Fi router.
So the data link layer is all about local delivery. It takes that packet from layer 3 and wraps it in something called a frame. This frame contains the physical hardware addresses, the MAC addresses of the devices on your local network. It's like the IP address got the letter to the right apartment building, but the MAC address gets it to the right mailbox. It also adds a little trailer at the end to check for errors.
And finally, we've hit rock bottom, the physical layer. This is where it all gets real. This layer takes that digital frame and translates it into a raw stream of ones and zeros, a bit stream. Then it sends that stream out as electrical pulses down a copper cable, or flashes of light through a fiber optic line, or as radio waves through the air for Wi-Fi. It's the physical highway for our data. So let's just take a quick pause and see how this all connects to things you might have actually heard of. You can see protocols like HTTP and TCP up top, and you can see hardware like routers, switches, and cables fitting into the lower layers. This chart really helps connect those abstract ideas of layers to the real-world stuff that makes the internet go.
Okay, so after that whole journey, you're probably thinking that every network in the world is built perfectly following these 7 layers. But, and this is a big but, that's not actually the case. Here's the twist. The OSI model, as brilliant as it is more of a reference guide than a strict rulebook that people actually build to.
In the real world, the internet actually runs on a different, more streamlined model called TCP/IP. You can see here it's a bit simpler. It basically squashes the top 3 OSI layers into one application layer and the bottom 2 into a network access layer. It's just a more practical model that kind of grew up alongside the internet itself. So if we don't actually build with it, what's the point? Why do we still learn it? Well, that is the model's true power. Its legacy isn't in hardware or software. It's in our heads. It gives everyone, from students to senior network engineers, a common language and a clear roadmap to understand, discuss, and fix networks.
And that is the absolute bottom line. Even though we build networks using the TCP/IP model, we think, we learn, and we troubleshoot using the concepts from the OSI model. It's the conceptual backbone. It's the grammar of how networks talk.
So I'll just leave you with this final thought. The OSI model might have lost the protocol war to TCP/IP, but its ideas are more alive than ever. And maybe that's because having a good, clear map is always useful, even if the roads and the highways change a little bit over time. It gives us a framework to understand the entire journey. Thanks for watching.